Hello, my name is Anthony Pellegrino. With my class project, I'm going to be going over chapter 9. So first, I'm going to start off by talking about two proportion problems. And in this type of problem, we're going to be discussing how to test a claim made about two population proportions. In order to test a claim made about two population proportions, there's three requirements that have to be fulfilled. So first, there has to be a simple random sample, meaning each member of the subset has an equal probability of being chosen. And two, the two samples must be independent, meaning the samples are not affecting each other in any way, and are not paired. And three, there must be at least 5 failures. So basically, we're trying to test to see which of the two proportions is more effective, or in other words, has a higher success rate. So for example, let's start off by talking about um, how we're trying to decide or to see if there's a difference between the success rate of a new the common morphine drug and a new drug that is supposedly better than it, because it has less side effects. So let's say the proportion of successes equals the drug not being addictive. So this is what it would look like. The morphine is P1 and the new drug is P2. So for morphine, we can say 102 people out of the tested 299 randomly selected subjects were addicted to it. So that would equal 0.341. And for the new drug, P2 would equal 56 out of the sample 307 people were found to be addicted to it. So that would equal 0.182. So for this problem, we're using a 0.05 significance level. And the p-value to test this is saying that, so for this problem, we're using a 0.5 significance level, and we're using the p-value to test the claim that there's no difference in success rates between the two treatment groups. So the claim can be written as, for the null hypothesis, H0 equals P1 equals P2, and the alternative hypothesis would be H1 equals P1, which does not equal P2. So to find the mean value between both of them, we would use the formula P equals, or the mean P equals x1 plus x2 all over n1 plus n2. So then once you put in those values, it would be 102 plus 56 over 299 plus 307, and we would get 0.2607. And now after this, we're going to be solving to find a test statistic, but in the formula for the test statistic, we also need the Q value, and we find that by subtracting this value right here, the mean, by 1. So 1 minus 0.2607 equals 0.7393, which equals again the Q value, which we're going to plug into the test statistic, which is what we're going to solve for next. So for the test statistic, we're going to be using the formula Z equals p hat minus 1 minus p hat 2 minus p1 minus p2 all over the square root of the mean p times the mean q over n1 plus mean p times mean q all over n2. So once you plug in the data, we would have 102 over 299 minus 56 over 307 all over the square root of 0.2607 times 0.7393 divided by 299 plus 0.2607 times 0.7393 over 307. So once you calculate that, that would come out to be 4.449 for the test statistic. So now that we have the test statistic, we can find the p-value with this. So after looking at the A2 table, we can see that the p-value equals 0. And since the p-value equals 0, and it's less than the significance level of 0.05, we can conclude that we reject the null hypothesis. So we can safely say now that there is a difference between whether the drug is more addictive or not, because we rejected the null hypothesis, which stated that P1 equals P2. So we rejected that. So we can safely say that there is a difference. So next, I'm going to be moving on to another problem that has to do with two means with independent samples. So I've already kind of touched on independent samples and how they don't affect each other, but how do you really tell what separates an independent sample from a dependent sample? Well, an example of a dependent sample would include something like the shoe sizes of a brother and sister. The sample is dependent because the size of each brother's shoe is matched with this shoe size of their sister. So that kind of shows you just how they're different. So here's an example of an independent test with two means. So listed in this data set are the weights of Americans that are randomly selected in the 1980s versus 2010. So the first step we would have to do is realize that the claim is that the mean weight in 1980 is less than the mean weight in 2010. So that could be expressed as mean 1 is less than mean 2. So in step 2, we would just say that if the original claim is false, then mean 1 would be greater than or equal than mean 2. So how that would look is, for the null hypothesis, is mean 1 equals mean 2, and the alternative would be mean 1 is less than or greater to less than or equal to mean 2. So to find the test statistic now, we would use the formula mean 1 minus mean 2 minus mean 1 minus mean 2 would just equal 0. And then that would be all divided by the square root of S2, which is the S's stand for standard deviation. So S squared 1 divided by N1 plus S squared 2 divided by N2. So after you solve for the mean of x1 and x2, you would see that that would equal 170.083 minus 192.167. Then that would all be over the square root of 6.3455 squared divided by 12 plus 10.4519 squared divided by 12. So after calculating that, that would equal 6.25649. So now that we have the test statistic, we need to look at the A3 table, which maps out the t-distribution to find the p-value. So also to find the p-value, not only do we need the test statistic, but we also need the degrees of freedom. So degrees of freedom is just simply n minus 1, which is 12 minus 1, which equals 11. So after looking at the t-distribution table, we can find out that the p equals 3.2313. Just to make sure that the p-value is accurate, you can also check it by going on your calculator and going to stats, tests, to t-test, and then enter the data. Then you will get the p-value as well as the test statistic, just to confirm that it's accurate. So to sum up this problem, we can conclude that there is not sufficient evidence to support the claim that the mean weight of American men in 1980 was less than 2010, even though the data portrays an increase in weight. The data does not provide enough evidence to support the claim, and this could be because may not be a large enough sample to show this. So for our next problem, we're going to be finding the constructing a confidence interval. So the confidence interval displays the probability that a parameter will fall between a pair of values around the mean. So in other words, it sort of indicates where the population parameter is likely to reside. So in this section, we're going to be trying to test the sample. We're going to be trying to test the same data set, except the same data set of American weights in 1980 versus 2010. But now we're just going to be using a confidence interval with that. So the formula to find the confidence interval is x1 minus x2 minus e, which is the margin of error, is less than mean 1 minus mean 2, which is less than x1 minus x2 plus e. So that now that we know the formula to find the confidence interval, we can easily find the x1 mean and x2 mean, but the most challenging part is finding the e, which is the margin of error. So that formula is ta/2 times square root s squared 1 divided by n1 plus s squared 2 divided by n2, sorry. So that would equal 1.796 times the square root of 6.3455 squared divided by 12 plus 10.4519 squared divided by 12. So to find the TA over 2, which equals 1.796, we could find this by using the A3 table. And then we already know the S and N, the standard deviation and number of values. So after calculating this, we would find out that this would equal 6.33925. So now that we have the E, it's really just smooth sailing from here. We can just plug in the values in the formula, and we should get the confidence interval. So again, the formula for the margin of error is x1 minus x2 minus E is less than mean 1 minus mean 2, which is less than x1 minus x2 plus E. So now we plug in the means of the two data sets, which was 170.083 minus 192.667, and then minus the margin of error, which was 6.33925, is less than mean 1 minus mean 2, is less than 170.083 minus 192.1667 plus, well, yeah, now we're adding the margin of error, so plus 6.33926 or 925. So after calculating that, we can find that that would come out to be negative 28.423 is less than mean 1 minus mean 2 is less than negative 15.74. So in conclusion, because the confidence interval does not contain a 0, the interval supports the conclusion found with the hypothesis test. So for my last problem, I'm going to be discussing confidence intervals for matched pairs. So for these types of problems, there are 3 requirements that have to be fulfilled in order to accurately solve it. So first, the sample data has to be matched pairs. And secondly, the matched pairs need to be a simple random sample. And lastly, the number of pairs of sample data has to be greater than 30. So now that we get that covered, let's move on to the problem. So in this problem, we're going to be testing to see if people are telling the truth about how tall they actually are. So listed in the data set are reported heights of random male subjects, and so for the purposes of calculating, I put a decimal between the feet and inches, and the significance level is 0.10. So first, let's just make sure that the 3 requirements are fulfilled. So 1, the data are matched pairs from the same subject. 2, there is random selection, and 3, there are no outliers, and it seems to be in a straight line pattern, so the distribution is normal. So now we can identify that the claim is that the mean differences are greater than 0 inches, and the null hypothesis would be that the mean differences equal 0, and the alternative would be that the mean differences is greater than 0. So now we're going to find the test statistic, and to find that, we need to know that the number of subjects is 10, and through a little addition and subtraction, we can find that the mean difference is negative 0.17. And the mean difference is negative because we subtracted the lesser measured values by the higher reported values. So the last piece of information we need to find the test statistic is the standard deviation, which is 0.67495. And to check your work, you can enter the differences into the L1 column, then go to stat, calc, enter 1 var stat, and you will see the mean differences and the standard deviation. So the formula for the test statistic is T equals mean difference minus the mean difference, which would just be 0, and then all over the standard deviation divided by the square root of n. So after plugging in those values, we would get negative 0.17 all over 0.67495 divided by the square root of 10, and that would come out to be negative 0.79648. So now we can find the p-value by looking at the A3 table, which is the t-distribution table. So when looking at the A3 table, we can see that, again, our degrees of freedom is n minus 1, which equals 9. So we look at the ninth row on the table, and even though our test statistic is a negative value, it can also be positive value because the t-distribution is symmetric. So as you can see, even though it's negative, it can also be positive. So on with finding the p-value, the degrees of freedom is 9, and the test statistic is negative or positive 0.7965. So that equates to an area in one tail, which is greater than the significance level of 0.05. So the p-value is actually greater than 0.05. And just to confirm the p-value is greater than 0.05, as well as confirming the test statistic, you could go on your calculator and use calc command stats, tests, and select t-test. So that's it for this problem. Let's just go over quickly what we learned today. We learned about testing a claim made about two proportions. We also learned how to test a claim made about an independent sample with two means. And lastly, we learned about confidence intervals for matched pairs. So thanks for listening, and I hope you learned something.